days for me, and it's a pleasure to be back. In the meantime, you probably had a better lecture on Tuesday anyway, because Ed was extremely nervous to do a good job for you guys. So hopefully he did all right, and you learned a little bit about ray tracing. So your homework, 3 is due this evening, and the next one should go out if it isn't out already, which will cover ray tracing. This is one of the more fun assignments, at least according to previous students. I mean, at the end of the day, ray tracing is not so bad to implement, and there are lots of different ways to extend. But I think I mentioned to you guys before that if you're looking for extra credit, and like maybe some of the past assignments haven't gone too well or whatever, this is probably a good one to think about for that, because I think there's a lot of ways you can extend the ray tracer that are relatively painless. Yeah? Your exam continues to slowly sneak up. I've gotten a few emails with questions. It's during class on whatever day it is. It's in the calendar. If I say it, I'm going to get it wrong. And so it'll be an hour and a half, just like classes. I guess minus 10 minutes for 500%. I'll post previous year's exams at some point. And I make no promises as to the difficulty level because I'm really bad at calibrating that. But we will, of course, not punish everybody in this class if our marks like yes. So that's the basic stuff. Are there any questions about just ongoing 837 stuff? Cool. All right, so today we're going to talk about acceleration structures for ray tracing, kind of picking up where Ed left off in our last lectures. Right? So as a quick recap, our ray tracing algorithm looks something like the schematic we have on the screen here. Right? That essentially, we have this trace ray function, which is sort of the center of our whole ray tracer, unsurprisingly, given its name. And essentially, its job in life is after you've figured out that you intersect with the shape, now you're going to send all these secondary rays to do things like figure out if you're in a shadow, or maybe a reflect array if you're in a mirror, or if you're transparent, or I guess then maybe you refract. And with every single one of these, you just generate more rays. But the basic primitive of the ray tracer is just this one function that says, I put in an array, and you tell me what it hits into first. Right? And the cool thing is that, like with very simple extensions, you can get effects like shadows and transparency and so on without too much excruciating pain. This is different from when we talk about GPU programming, like video game style rendering, where like if you want shadows, you have to implement an entire shadow pipeline. This is a completely different thing. If you want reflection, then you have to have a reflection code. And if you want, I don't know, to figure out what's that video game with the guy that jumped through the holes and ends up in other places? Portal, that's Portal is like this amazing feat of shader coding, which I believe actually Cornell, they make their students code in the graphics class, which is really painful. Yes?
It's like NVIDIA's like YCX trying to make it more like Mac video.
Yeah, so there's this push-pull that happens in the graphics world where like every other year we decide we really want to do real-time ray tracing on the GPU, and then every other year we say, well, ray tracing isn't that bad, it's not something we want to rasterize. So I don't know the particular NVIDIA hardware this year, but they walk a funny line, and of course nowadays NVIDIA could care less. They're mostly trying to get the deep learning market to be excited and more aware of this is an interesting time to be in the graphics card business. But in any event, our images in lecture will not look like the beautiful NVIDIA demos they have, but rather 3 really ugly balls sitting in front of a mirror, and we're going to try and capture that effect for now, and then of course expand more as we move along. Right? So as of 2 lectures ago, if you tried to render this scene, you would see these nice diffuse objects and black mirrors behind them. And unless you're working for Netflix, this is probably not the image you want, but rather you'd like to see some nice reflection that goes through these things. Right? And the basic idea of ray tracing is that it's a recursive algorithm. Right? If my ray hits into the mirror, then I reflect it, I call again, and it renders the rest of the scene. But you have to be careful because, of course, recursion can be infinite. Right? And so to avoid that scenario, typically we kind of cap the number of times that you recurse, and you just have to return blank or something for your rate. And so at the end of the day, a nice visualization for this, which I think Ed mentioned in his lecture, is an object called the ray tree. This is not like, I think as computer scientists, we're used to hearing the term tree and thinking of it as a thing that we would code. This is not that. This is like just a thing that you look at to visualize what's going on in your ray tracer. And the main thing that you should get out of this image is just the amazing complexity that goes into rendering a single pixel. Right? Do you guys see that? So the white line here is kind of like the line from your eye into the world. And then essentially what you're seeing, all these different lines are all the different branches that take place in the ray tracing algorithm. Right? So for example, here there's some reflective component, some refractive component, and it hits the bottom, and there's total internal reflection, and there's also refractive, or whatever. And so just to generate this one pixel color requires what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4. A lot of rays. And this gets really slow quite quickly. Yeah? And in case this wasn't slow enough, of course, one thing that was mentioned briefly at the end of the last lecture is that ray tracing is sort of this nice distributed algorithm, and that basically our solution to all problems is to generate more arrays. Right? I think that's really what we've seen so far. And so effects like soft shadows, anti-aliasing, glossy reflection, motion blur, right? Each one of these things, basically at some computational cost, you can get just by, again, wrapping code around a basic intersect array with the world's operation. Right? So as some examples, right? The ray tracing shadows that you guys will implement on your homework will all be extremely hard shadows, right? That means that there's like a sharp line. And that makes sense, right? Like if I have a point light and I shine it on an object, then there's like, you can just see the corner of the object on beneath it. But of course, in the real world, if you look underneath you, there are very few shadows that are really that sharp, right? And so the reality is that light tends to be emitted from light sources that are kind of chunky, right? They're not just a point. And so how could we simulate that? Well, one way to do it is instead of sending just one shadow ray, send a bunch, right, to different locations on the light source and then average the result back in, right? And of course, as a piece of code, hopefully you guys see, this is pretty straightforward, right? You just generate a bunch of points in the light source and keep generating new shadow rays. But what happens? The more detailed or nice looking the shadow you get, the more CPU time you have to spend, right? Or similarly, for motion blur, if I want to have like a really dramatic ball pit, actually the physics of this image like really weirds me out. Like I think whoever rendered it got it kind of wrong, right? The balls are moving really quickly until they hit the ball pit, and then somehow they're moving more slowly. Anyway, but that aside, how could you capture that effect? Well, one thing to do would be to ray trace a bunch of times with a bunch of different positions for the ball. Right? But again, what happens? You took the complexity of your ray tracer and you multiplied it by the number of positions you want to ray trace. Yeah? And so the basic problem that we're going to address today is that there are just too darn many rays in your ray tracer. Right? And so that little segment of code that just takes as input array and outputs what it hits into is so critical that it's worth optimizing the bejesus out of it if we're going to code up a ray tracer in practice. Does that make sense? And in fact, like, if you took, what's the algorithms class here? At CS 161 at Stanford, I'm sorry, I don't know. 006, right? You would do, if you actually did your algorithms analysis, you see it's pretty terrible for ray tracing, right? I mean, it looks something like this, right? Your complexity is like the width times the height of the image times the number of primitives times the cost of an intersection times the size of your ray tray, and so on, right? And these are multiplicative factors, right? Because every single time you branch out the new ray, you have to extend this whole procedure over. Yeah? So it's easy to get a really beautifully ray traced image. It's just slow. Okay, so that's our motivation for the day, is how do we do this stuff quickly, and we're going to talk about a few different tricks to do this, many of which are probably pretty obvious in a sense that, like, I think if I asked a lot of you guys as CS students to come up with sneaky ways to make a ray tracer faster, you would cook up something like this. But there are a few kind of standard terms that are worth knowing and implementing. Okay? Okay. Right, and in fact, rather than even accelerating ray tracing, of course, accelerating ray casting, just that one ray scene intersection operation is kind of enough to really get a big benefit. So actually, you guys tell me, what would you do? So let's say I'm rendering this bunny. The bunny's composed, if I recall, of 1,336 triangles, and currently, what would be the complexity of this algorithm? It would be the number of pixels in my image times the number of triangles on the bunny. Not so great. So how can I speed that up? The wall seems to want to participate. Nobody else is. There's no wrong answer. There's a lot of ways to speed up ray tracing. Yeah. Yeah, you can narrow down which triangles you're likely to intersect, right? Or in other words, cull out stuff that you're likely to intersect against. Any ideas how would we do that? Rose.
I guess in this specific example, we know that all this volume is concentrated in a specific subset of the entire volume that you're looking at. So if you were to somehow build slash what exactly you potentially apply
Yeah.
to, that would make a lot more sense out of machine errors, right?
So just kind of subdividing space a little bit and culling out big pieces. Yeah,
And
that's a
like
great idea.
maybe, I don't know. So like in previous lectures, we always see that we're like breaking down, let's say, bodies into like a true hierarchy. Maybe in this case, we could do something similar with respect to like X, Y, and Z.
Ah, that's great, and that's actually a strategy we'll cover later in this lecture. Yeah. Any other ideas? A lot of ways to speed up variations. Yeah? Yeah, sure. That's called backface culling, right? You just throw away triangles that are pointing away. I challenge you to come up with a data structure so that you can only come up with a list of the triangles that face toward an array without looking at all the triangles. It's not impossible, but it's tricky. You can parallelize, right? You can just throw a bunch of CPUs in your computer. It's a perfectly valid way to speed up a ray tracer. In fact, actually probably one of the most efficient. So anyway, there's plenty of things to do. Or you could have multiple resolutions of the same bunny, and maybe if it's far away, render the low resolution one. Yeah. So let's actually start with Emily's suggestion today, and talk about just culling out rays. Right? Putting I think it was Emily that suggested that. I'll put words in your mouth. So right. In other words, just understanding that there are lots of objects in the scene. And if we don't get anywhere close to an object, we certainly don't need to intersect with every little detail of that thing. And so, right, so the simplest thing to do would be to put a giant box around the bunny. Yeah? And if your array doesn't intersect the giant box, then don't intersect with any of the triangles inside of the bunny. And it sounds like a stupid scene, but it's a stupid thing to do, but if my scene has 1,000 bunnies in it, and every bunny has like many thousand vertices, I've just created a series of many thousand potentially. See that? Because I think one of the things that's worth noting is that in ray tracing, it's really hard to control the density of stuff per pixel, and it often is extremely variable across the scene. Right? So for instance, maybe I have like a bunny in the distance, like running toward the bunny or something, and then it could be that all these triangles are like sitting inside of 3 pixels, right? So I could either incur for every single pixel on my image, array bunny intersection, or I could very quickly cull it. And so, what do I have to do? Well, I have to come up with some conservative bounding mode, right? And that's like a volume of space that contains your object. Okay? And of course, there are many options, right? So the simplest thing to do is put a rectangle around your shape. You can also surround it with a rotated rectangle or a sphere or what have you. Essentially, the basic concept here is to have some object that's as tight as possible that fits under this thing, but it's still easy to intersect with. Does that make sense? In fact, a standard trick you can do is maybe you have a bounding cube and a bounding sphere for your bunny, and you intersect them both. And that way, for cube-like objects, you do okay, and for that's perfectly fine. Yeah. So why do we like this? Well, obviously, if my ray doesn't even go anywhere near the sphere, I don't have to intersect with anything inside of it. And furthermore, ray-sphere intersection is pretty straightforward. Right? It's just a formula. Yeah, and that's what we're looking for. So as an example, probably the most standard thing to do is to use an axis-aligned box. That's exactly what it sounds like, right? So you say that the bunny has a range of x values between these 2 things, a range of y values between these 2 things, a range of z values between these 2 things, and then if your ray just doesn't ever touch that box, then you have the intersecting inside of it. And let's work out a little bit of detail of what ray box intersection looks like. And again, I think all of you guys could do this at home, but it is worth thinking about a little bit just in terms of how could I do this as quickly as possible. Because remember that even if you have some really lame piece of savings where you're coding up your ray tracer, like what are these commands in C++ where you kind of do 2 adds at one time and using the 2 sides of your ALU? Anyway, there are all kinds of things that you can do to just speed up your computation a tiny bit, but these get multiplied by huge numbers, right? Because there are just a lot of rays. So even thinking carefully about ray box intersection, because there's a lot of boxes in your scene, is a pretty worthwhile exercise. Yeah. Okay, so let's say that my box is the x1, y1, z1 to x2, y2, z2 range. So in other words, x is between x1 and x2, y is between y1 and y2, and so on. And my array, as usual, is r0 plus t times the direction. Well, of course, the most naive thing I can do is a couple lectures ago we talked about intersecting an array with a plane, right? And a box is nothing more than intersection of a bunch of half planes, right? So I could do something kind of similar to what we did in the CSG lecture, right? Just start cutting off half planes and returning something if that intersection is not empty. And that's more or less what we're going to do here, but we can speed it up by just doing a few additional tricks. Okay? So there's a couple observations that can reduce the amount of work that we have to do. And again, I know this feels like Donald Knuth style, old style computer science, where you're counting precisely the number of adds and multiplies that happen inside of your box array intersection, but it's worth it because you remove one of those, and that's a ton of computation you can actually reduce. Can't say that. Okay. So some ways to reduce the computation. One is that, of course, pairs of planes have the same normal. Remember that when we did plane ray intersection, there's a dot product of the normal to the plane that happens in there, so we don't have to compute that once. And if the planes are axis aligned, then in fact they only have one non-zero component, so we can throw away 2 multiplies that way. That makes sense? Because your normal is either 1, 0, 0, 0, 1, 0, 0, 0, 1. Yeah. And we'll do one additional trick too. Incidentally, one special case you should worry about is when your rate is parallel to your box, but I'll let you know. Okay, so probably the simplest thing to do, and of course what we do in practice, really does look like CSG, right? So essentially what we're going to do is look at one axis at a time and intersect 1 to 1D intervals, and if that intersection is empty, then we know we don't have to look inside the box. Right, so for instance, let's say that we have the range from x1 to x2, and I have my ray, remember that's the origin, plus t times the direction. Okay, so what are we going to do? Well, we'll compute first just this blue bar, which is all of the range of t values where you're inside of that range. Right, and then maybe I cut it a second time with the green bar, which is all the times you're in the y range. Right, what you're left with is the purple intersection. Okay? And of course, like we talked about in our CSG lecture, if we have a bunch, right, so the x-axis here is time, right, and this is like the time where you're inside of the x planes, the time where you're inside of the y planes, the time inside of the z planes. Well, what do I do if I want the intersection? What is the left-hand side of the intersection, assuming that it's not empty? It's the max of the mins. Does that make sense? So every interval is from a min to a max in the range here. And so if I intersect, the left part of my range is the max of all the min values. What's the right part of my range? The min of all the max values, yeah? Sorry, I didn't see your hand. Right. And so in fact, one thing I could do would be compute these 3 intervals, take the max of all the mins, min of all the max, and when is this interval not empty? It's when the max of the mins is less than the min of the maxes. I had a lot of people in my office hours this morning with bizarre logic mistakes in their code. I won't call them out today. But I would say this is a great source of those kinds of effects. So be really careful when you code these things up. Okay. Right. So anyway, there's our nice interval, and in this case it's not empty. Right? So in other words, if start is bigger than end, the intersection is not empty, otherwise not. Okay. So essentially, our job then reduces to just finding T1 and T2 for our 3 dimensions, and of course, that's nothing more than just one-dimensional math, right? So at the end of the day, the x coordinate of my ray, right? Ray x of time is equal to r 0x plus time r direction x, right? And so if I'm trying to find the time when that thing equals x1, I just have to solve this equation. Right, this is marginally simpler than what we did 2 lectures ago, where you had an x, y, and z component, right? Because I'm assuming now that we're just in x. And so, of course, that means that t is equal to x1 minus r0x divided by r dx, which, if there's a dot, is what's on the slide here. Yep. And so that's just how you get your range of t. Yep. So at the end of the day, there's just 3 different formulas. You intersect, and then you're good. Okay? And that gives you the range of t values for your array. Of course, you have to be a little bit careful. There's one case that you have to worry about, right? After you find this intersection here. I think we animate. We've got a little crazy with PowerPoint animation. Right. Which is now we have to figure out, do I actually have to ray trace inside the box or not, right? And there's a couple cases, right? So for one, if t start is greater than t end, right, then I don't actually intersect that box. Is that the only time that I can do anything? If I compute that intersection of intervals? When else can I call out this box? What if my eye is like still pointing this way, but he's like sitting right there? So the array still intersects the box, but the t values are all negative, right? Then I still don't have to. Right? So in other words, there's some t min, oftentimes 0, but not always in your ray tracer. And if the intersection of the intervals, which of course it ends at tn, is less than t min, then you don't have to ray trace either. Even though, notice that the ray intersects the box. See that? This is the kind of fun logic that you have to do when you think through these kinds of things. Yeah? So you have to be careful. So the boxes that we've defined are bounding boxes, right? Which means that I don't actually render the box, I render stuff inside of the box. Yeah? So even if I'm in this scenario where like I have, here's my eye, and here's a box, here's another one, and the array curves a little bit because I'm bad at drawing, and it intersects both of these boxes. You're saying, like, can I just eliminate this guy because he's scared? And the answer is actually no, right? I could be unlucky. Like maybe I'm ray tracing a donut, and my donut has a little hole right there. Right? So this is still the bounding box, but the ray has to go right down the middle of the donut. However, one thing I could do is compute all the ray box intersections and order them from back to front, right? And say, well, if I intersect this front guy, then I don't have to lie. Right? We'll talk about that in a minute. Okay. Right. And then the third case you should be a little careful about is when the eye is inside the box. And when the eye is inside the box, then you got to ray trace the box. Okay. So at the end of the day, actually, even this pretty simple little operation of intersecting array with the box is something that requires a little piece of code that you should be careful how you implement and try to eliminate as many adds and multiplies as you can as possible, because this is going to get called billions upon billions of times in your ray tracer. Right? In fact, that's one of the kind of fun things about writing graphics code. Like when I've worked in a graphics company, every once in a while, I'll like check in some stupid bug fix for like how pixels are converted from RGB to HSV. And somehow, philosophically, it's very exciting that your little piece of code gets called trillions of times a day. It's only because there's just a lot of pixels in an image, you know. It's heartening to me. Right. So, in case you thought this was the only number of efficiency tricks you can throw at this problem, you'd be wrong. One thing to know is that divide is a little slower than multiply. So oftentimes people will do all kinds of hacks, like pre-compute 1 over these R's because they show up in more than one of these programs and so on. Right? And if you read graphics code, that's why it often looks really disgusting, right? Because people will very, very carefully optimize and try and factor their expressions in just the right way to remove a few adds and multiplies, but it makes their ray tracer consistent. Incidentally, oftentimes students, when I take this class, will say, oh, I'm not going to bother doing that because C++ is really good at optimizing my code, and so I'll just roll out C++ to do that. The reality is, in code like this, that's very unlikely to be true. Although I guess more so maybe now than it used to be. That essentially, so like for example, let's say that I have A times B, and then I have another expression which is A times 1 over B, and I have A divided by B, right? And I parenthesize it like that. Of course, you know, if we're in elementary school, these two things were the same. But the reality is, these are not the same with respect to double precision floating point, right? Like here, I introduced potential error by computing reciprocal and then multiplying, right? So when I use my compiler, remember compilers are optimized for predictability, right? That like yeah, they're trying to make your code fast, but they always want to obey what you told the computer to do, right? And this is an unsafe change because it affects the output of your program. You see that? And so these kinds of mathematical tricks, which probably don't matter to us in our ray tracer, because we only really care about the first few bits of precision, your eye can't see anything beyond that, probably won't get picked up by your compiler because it doesn't know that it's okay to make these kind of changes. Yeah? Of course, there are ways to enable that. Like there's a favorite among a lot of graphics programmers, if you use GCC, is this -f unsafe math But just the name of that should have you look scared, right? But that is a pretty standard thing. Okay. So computing the bounding box of a shape is like a really, really easy thing to do, right? If it's axis aligned, you just take the min of all the x values and the max of all the x values, and so on for y and z. For some reason, the slides of this class go excruciatingly slowly through all kinds of different primitive shapes. Are we okay if I kind of skip this? Yeah. Okay. I'll let you guys check at home that you can compute the bounding box of a circle by taking the middle. Okay. One thing to notice, by the way, which is not, which I think is abundantly obvious, but easy to get wrong if we're not thinking carefully. This is the theme of a lot of ray tracing. If I rotate a box, its bounding box does not rotate if it's axis aligned. Do you see that? So if I have, for example, a square, and I rotate it to a 45-degree square, its axis aligned bounding box screwed, right? Because it's axis aligned. Okay, so when you apply a transformation to a shape, then you need to compute the bounding box and the original coordinates, so you need to be a little careful. Okay. Of course, there are rotated bounding boxes. That's the thing that people do, in which case you don't need to worry about that. It's just a way. It also means, by the way, that the axis-aligned bounding boxes, although they do help a lot, are all a little funny, right? Because if I have a 45-degree rotated shape, it might help me a lot less because my bounding box is a lot bigger than it needs to be. Because the real world is not axis-aligned. Okay. So here's my next question. Now that we've done the most excruciatingly boring calculation we can in the box, is this enough? So let's say that I just implement a bounding sphere for this bunny here, and maybe I subdivided the surface of the bunny. It has a million triangles in him. The bunny only takes up 1/8 of my computer screen, so effectively I've eliminated 7/8 of my computation. Pretty good. Is that the best I can do? No, why not? Exactly. There's no reason why I have to put one big circle around the whole bunny, right? I could put a circle around the left side and the right hand side, and maybe that way I can divide my computation in half, right? In fact, I could do all kinds of crazy things, right? I could have a whole hierarchy that says I'm going to put one big sphere around the whole bunny, and if I don't intersect that sphere, I'm done. If I do, then I'm going to look at two spheres inside of the bunny that divide it in half, and do that recursively, right? And this idea is called a bounding volume hierarchy. The idea that I can nest bounding objects inside of bounding objects inside of bounding objects, and all the way at the bottom I do my triangle intersection, but until then I can continue to close that out. Okay? And this is really important for all kinds of reasons, right? I mean, if I have a video game with levels, and the level has things inside of it that are detailed and so on, then maybe I have a whole recursive structure for containing stuff. Yeah? I'm sorry for that. I guess this is the heater in the wall. Okay. Right, and so this leads to this idea of a bounding volume hierarchy, BVH. Yeah? And this is a key idea in the rendering world, both in ray tracing and in rasterization. Yeah? Because in rasterization, right, I have a similar trick where maybe I'm just rasterizing an image that sits over here, in which case I don't rasterize any of these triangles. Okay? By the way, there are all kinds of sneaky tricks that people used to design video games so that these algorithms were successful. Did you know this? So for instance, oftentimes you have these levels. I think in Doom is a good example, where like your floor plan of your video game is like this. This like little itty-bitty door stuck in the corner of the room. Right, so here's your door. And why would you do that? Well, you now have this giant wall obscuring everything on the other side, right? And so you knew that you didn't have to render this sun, even though you have an open door, so there's some amount of triple treatment to see. It's really sneaky. Actually, the hardware used to inform how people design video games. But anyway, so right. So the idea of bounding volume hierarchy is maybe I have all the triangles in my scene. I put a big bounding box around those, and now I take that set of triangles and divide it in half. I put a big bounding box around those, and do that recursively. Yeah? And there are many, many ways to do that. And at the end of the day, it leads to a binary tree data structure. Not all like what we saw in hierarchy. So for instance, here's the scene, I divide on the dotted line, and now that gives me two bounding boxes. Notice that there's some space in between them in this case, so that's kind of nice. And now I can take these two bounding boxes, divide them horizontally, and do, yeah? Okay, so there's another one. What happened in this level of my tree? You guys see something that's going to be a little bit irritating when we code? That this box and this box intersect each other? And there's kind of no way around that under the assumption that I'm going to put a triangle in only one box. See that? Okay, so that's we're gonna think about that for a minute. We'll continue to solve it. Okay. Right. So of course there are a lot of different questions. One of them is just how do you build this tree? Like where should I put that split line? I think a pretty typical thing to do is to kind of sweep the split line up the side of the box a little bit until you find some location that roughly splits it into two sets of equal size. And so it just involves sorting by like the one coordinate and choosing in the middle. Yeah. But there are all kinds of different tricks people use. By the way, oftentimes you can afford, like, so if you think about, there's a term in computational geometry which is relevant here, and it's called amortization. Also shows up in mortgages. Yeah. And so the idea of amortized computation is that let's think about the way that I code my ray tracer. This is stuff that happens before I ray trace and the stuff that happens during the ray trace. You see that? Like, so for instance, building this bounding volume hierarchy is not a per pixel thing, right? This just happens once before I begin ray tracing. I analyze my scene, build up this tree, and then I ray trace. So if you think about it, this is kind of an interesting trade-off that happens, right? I can put a lot of time into making a really, really good hierarchy and then effectively reduce my ray trace time. But what did I pay instead? I paid because I had to spend more time building the hierarchy. Yeah? And so oftentimes the way that we think about this in computational geometry, this idea of amortization, is that really the runtime that matters for building the BVH is the runtime of the BVH divided by the number of pixels. You see that? Because that's really like the time per pixel which is going to affect your ray tracer. Yeah? So in other words, it might be that if you have a really, really detailed image, it's worthwhile to build up a fancier hierarchy than a very low coarse. Yeah? But I think the usual rule of thumb is that the cost of building these things is so much lower than the cost of ray tracing. You can afford some pretty fancy geometry here. I think it's going to save you some time. Okay, but anyway, there are all kinds of different ways to build BVH, and I think recursive split is a pretty reasonable one. So now we should talk about how to intersect array with this object. Yep. So again, remember our basic data structure here is this going to be like a rectangle, and then inside of every rectangle is two more rectangles. Yeah, until I get to that problem. Okay, and the thing to remember is that those two more rectangles may intersect each other. Right? You don't always get so. Okay. So here's our array, here's our big orange BVH. You know, we've decided our array intersects that box. We now know how to intersect rays and boxes. That's what we did at the beginning of the lecture. So that means that we have to intersect this guy with the two boxes inside. In the case that we have to worry about, this is the most evil test case. Do you guys see what happened here? So, like for instance, one thing you might say is like, okay, I'm going to hit this box first. I forget somebody asked this. So maybe I can ignore the one in the back. But take a look at this really evil thing that I did. So the blue stuff is the back box. The yellow stuff is the front box. I intersect the front box first. And in fact, I intersect something inside of the front box, this yellow triangle. But it's still the case that I intersect the blue guy first, even though he's in the box that's not far away. Yeah? So what does this indicate? This means that I really do have to intersect my array with both of the boxes inside of my bounding hierarchy. Listen, I'm very careful. Yeah? But there's one sneaky trick, right? So here's the intersection. So let's say that I intersected with the front box, and the T of my intersection was before the first T of the second box. Then I could be confident of not intersecting the second. Does that make sense? So in other words, I intersected a triangle like in this area here. So anyway, these are just the kinds of things to think really, really, really carefully in the coding. And they're really subtle. And none of these are going to lead your code to crash. They're just going to make for weird redundancies and you have to debug. Right? And I think you guys have started experiencing this in the physics homework, right? The physics code doesn't often segfault. Well, it does for some of you, I discovered. But it doesn't, it oftentimes will just kind of fail quietly, right? You just get bad physical behavior. And so it's kind of a different kind of debugging thing to do. Okay. Right, so the advantages here is that it's relatively easy to construct and traverse these trees, but it may be hard to find a good split Like it might be that your two boxes inside overlap so much that you haven't really gained anything. And in that case, really, you actually added computation to your algorithm, right? Because now you have to intersect your array with all the triangles and go down to BPH, which is no fun. But it's still sort of recommended, you know, for your first hierarchy. This is relatively easy. Yeah.
So is this like, for example, that's how like you not render these that are behind walls?
Yeah. So if you have you know, you put so for instance, say I have a scene and it has the third one back here, right? And I have a bounding volume hierarchy that looks like that. Right, so it covers it. Well, if I have an array that's inside of here and it intersects this wall, I never need to look inside of this box over here, right? Because he's contained in his own piece of the hierarchy, which is so far away that I don't have to recurse any close to that direction. Right? And the reason that the T of this intersection before the T of the consensus.
So you have to check this object, not a hierarchy.
You got it. Yeah, so when you recurse down the hierarchy, you can't stop recursing until you actually run into something. Right? That's what this funny two triangle shows us. Right? You really can't look at it. Okay. So there's a small variation of this, which I think is more popular in practice, which says, okay, I'm going to have my boxes not overlap. Just by fiat. I'm going to say that the boxes in my tree can't overlap. But instead, I'm going to add an object to more than one box. Right? That's the other way to do it. And that data structure is called a KD tree. Okay? It stands for k-dimensional tree, so I guess k would equal 3 in this class. This is also used in machine learning, by the way. So if you have very high-dimensional data and you're like trying to do something like k-nearest neighbors or something where you have this big cloud of data points and you want to find something nearby, it's exactly the same structure that people use there. Okay, and this is probably the most popular one. Essentially, it's like a binary tree, but in this case, instead of having just a bunch of different boxes that are nested, what we have is like a plane. So you choose whether your plane is an X, Y, or Z, and then you kind of sweep it, and anything to the left of the plane is added to the left guy, anything to the right of the plane is added to the right guy, if you recurse. Okay? But the trick is that you add the same object to more than one node. So for instance, this image is a little too sneaky. This circle might be inside of these two boxes. And this is going to allow us to reduce the number of intersections we have to do. But now the space that my bounding volume hierarchy takes is much larger. Do you see that? Because I could potentially, like, let's say I got unlucky and I had a sphere like right here, right? Then I'd have to put it in this bin, this bin, this bin, this bin, in order to be confident that I intersect. Okay? So here's the typical data structure for KD trees. I'm a nice guy. I didn't add this to your ray tracing homework, but if you want to do a really cool extension, this is a fun one to implement. It's a really good way to introduce bugs into your code. Right. So the idea is that you have two different boxes here. We'll call them front and back, and those are also KD tree nodes, right? Because it's recursive. The int, that's the dimension split, would be like 0, 1, or 2 here. It just says whether I split on X, Y, or Z. And there's a split distance number, which is sort of the position on this axis that is the location of the split. Does that make sense? Incidentally, you could have a KD tree where the axes are not X, Y, or Z, but they're just some arbitrary plane. And that is something that people do. But it's just, again, it's just extra complication. So I think, like from an n log n perspective, it doesn't really save you much, so we don't typically do that. And then finally, maybe you have a list of triangles, which is just for leaf counts. Does the basic data structure make sense to everybody? Okay, cool. So we talk about two things, right? One is how to construct this thing, and the other is how to use it. Okay, so let's talk about construction first. So we start with the scene. And there's sort of two different decisions you have to make, right? One is which axis do I split, and the other is where I should place that plane. Yeah? This is pretty similar to the BBH. Right, so typically it's pretty easy to choose a relatively good dimension. I think the heuristic people typically choose is just the longest one. Although not necessarily, right? It could be that, like, what would be a good scene? Like maybe I have a bunch of books stacked on a table, like that. But they're really wide books. In which case the dimension is split on is probably this way, even though maybe the books are wide enough that this is the widest dimension. So yeah. But in any event. Right, but then we have to choose where to split. And then if an object like this triangle here intersects both, then we place it on both sides. Yeah. Okay. And then we recurse, right? So now we take all the guys on the left-hand side and we call the same function which says put this in a KD tree, but the KD tree really is a leaf of the guy. Yeah. Yeah.
So is there a reason that these are really used?
I mean, these are 3D plans, it's just hard to draw. Your instructor is really bad at PowerPoint.
Well, like, if it's a plane, does that mean it's just from one perspective, or is it actually like thousands?
Well, it's a plane in 3D. So the idea is that maybe the plane is like coming out on screen here, and everything on one side of that plane is on one branch of the tree, and everything on the other side is on the other. So I mean, you could put a box just because your scene is bounded, but that's not typically what you do. Yeah. So the picture that we draw, like here, here is maybe what you're referring to. Like, why is there a box here? Well, the reality is that this plane is going all the way up and down, but I've already recursed on this plane here, so I know that there's nothing above this thing. So implicitly it's a box, but from the tree's perspective, it's just.
So are there also
Like you're just worried about the z-axis?
Yeah.
Yeah. Here I'm showing you a KD tree for k equals 2.
Oh.
And that's just because it's hard to draw, but you're absolutely right. In 3D, you can do it. Yeah. Okay. And typically you recurse until there's some fixed number of primitives, and you say like, okay, we will pedantic to just have a triangle for a region in the tree. So maybe you have a few. That's okay. And that allows you to render these kinds of complex things. So there's all kinds of surveys and PhD theses written on efficient ways to construct KD trees. We have questions about how to construct a KD tree. Okay, so let's talk about how to traverse one. So now I have an array, and I want to figure out if it intersects the tree or not. And so the simplest thing I could do is just intersect with both sides, right? And say, well, if it intersects the front box, recurse. If it intersects the back box, recurse, and then take the closest thing. Right? But we might be able to do a little bit. So one thing you could do would be to have a bounding box for each of the children. That's unlikely to be terribly helpful because a bounding box is pretty similar to the tree you've already computed. So there's a little bit of slick math we can do instead. So the very first thing that we're going to do is intersect our array with 3 different planes. So one of the planes is the one that our KD tree keeps around. But then maybe on every leaf we additionally keep sort of the leftmost point and the rightmost point. So just like the total range of x values and the range of the point where we're going to split them. Right? Notice that's an easy number to keep around on your recurse. Okay. And now what can I do? Well, I can intersect the front box, the back box, and so on just by having these 3 values, right? So for instance, if t start is less than the t of your array, then you look at the front box, so leave the back. Yeah. And in fact, even though when I draw this picture, it looks like I don't have any savings in my KD tree, right? Like I still have to intersect the front and the back. That's not always the case. So for instance, here you can see cases where I only have to do the front or the back of the tree. Okay. So so if we have t start, t, and t end as our 3 t values, right? Then what can we figure out? We can say, well, if t is greater than t end, right? So in other words, let's see here. The time at which you hit the far plane is after the time at which you hit the middle plane. Did I do that right? The other way around. Yeah, so let's say I only intersect the front box. Okay? Then think about the ordering of the t values. Right? You hit the front guy, and then the next t value that I should include. Oh, I'm sorry, I'm being an idiot. Okay, let me back up a little bit. Sorry, your instructor is a little jet lagged. So, here's what you keep track of when you traverse your KD tree. My apologies. T start and T end are for the total time you spend in this cell of the KD tree. right? So at the very beginning of your computation, you have a bounding box around your entire scene, and that gives you the entire range of t values where you're just somewhere in the scene. Okay? And so when you recurse, those come as input to your recursion function. Because essentially your thing that you're recursing on is this entire cell, which is the union of these two bits. Sorry, I'm backing up a little bit. I apologize. But now you have one additional piece of information, which is this plane in the middle. Okay. And right, so what am I going to do? Well, I know now 3 t values, t start and t end, were my old ones, right, which tell me the whole time that I'm inside the box. And now t is the time when I intersect the plane that splits. And now the next diagram makes sense. My apologies. So let's take a look. So let's say I only intersect the front thing, right? And what are the labels of these 3 points? This is t start, right? What is this guy? T end. And this is, so in this case, you intersect only the front box when t is bigger than t end. Okay. Now, let's look at the back box, yeah? What is this guy? T star. So if t is less than t star, then I only intersect the back guy, and I don't have to look at the front box. Okay, this makes better sense. Okay. And what's this guy's label? T. Right. In this case, I'm host. I have to look at. Yeah. Okay. But I can be a little bit efficient in that, right? So in particular, let's say that I look at the front guy, and I notice that I hit this triangle. Do I need to recurse on the second guy? No. Okay. So now, right, all these labels make some sense. And finally, this thing, which somehow made it into someone's PhD thesis, which is impressive, is as follows, right? So essentially, we have a bunch of different cases. For one thing, if you're a leaf, you just have to intersect everything inside of that cell, right? No choice. And now, you have to enumerate a bunch of stuff, right? If t is less than t start, right, then I only have to intersect with the back. If t is greater than t end, you only intersect with the front. And otherwise, we have this sneaky thing where you first intersect with the front, and then if you hit something, you're done. And otherwise, you intersect with the back. So that's our little algorithm. You see, and this makes some pretty considerable sense. And notice the only reason I was able to do that is because I potentially put an object in more than one cell in my KB tree. So as an example, let me see if I can do this one. So let's say I have a KB tree like this, and my split is there, and I want to render a horseshoe. Okay? So our examples are going to get crazier and crazier today, so as we move on. Yeah? And let's say that I got really unlucky, and my array does that. Okay? Well, take a look at what happened here, right? As opposed to, so in this case, I really do have to add the horseshoe to both cells, because this algorithm is depending on the fact that I look at the front cell and then the back cell and vice versa, and intersecting. And otherwise, for instance, let's say that I did front and then back, and for this right here, and I determined like I don't hit the horseshoe, I'd be wrong. Right? So I really have to add it to both cells. Okay. Yeah.
How do you decide what the front and what the back is? Does the plane behave like the same direction as the array?
That's a great question. So I'm using the words front and back, but this is a little suspicious because I haven't told you where the ray is coming from. Right? The ray tracing happens after I construct the tree. You're absolutely right. Front and back are total misnomer too. In fact, these are just 2 leaves, and it's just stuff on one side of a plane and stuff on another. Like x smaller than t and x bigger than t, whatever t is. And we use the words front and back by first looking at the direction of the ray and figuring out like is the x direction of the ray positive or negative, and that determines which of these 2 guys is front and which one is back. Okay, so you might have to do that.
So how do you, so you can eliminate things from one side if they intersect like the first, other side, first,
Yeah.
right? So how do you do that without like having a constant?
Well, you do have a constant in front side. You just have to determine it in the process of doing the array box intersection, and it might change. So, for instance, here's my KD tree. Here's a triangle. Here's another triangle. If my array is going this way, this guy would be the front. If my array is going that way, this guy would be the front, right? And the way that I can determine that is that this axis, let's say, is x, right? then if I take a look at the x component of this vector here, it's positive, and the x component of that vector here is negative. Okay, so that's, so you have to, there's a little bit of a yeah, you're also right. All these details matter a lot. Any other questions? That's a great question. Okay. Cool. And so essentially, all of this stuff, if you think about it, is really depending on this one line of code here, this early termination, which is saying that like there's probably most of the rays of my scene hit almost all of the planes. Right? Like I'm looking at my scene head on, like, there's a lot of planes that probably intersects with. So really, this one if statement here, which is saying throw out stuff if it's already obscured, is helping me quite a bit. It looks insane. Okay. Right. And so this actually has an interesting property, which is it often allows raycasting to be kind of independent of the scene depth complexity. Depth complexity is kind of a cool vocabulary word. It says that like, depending on my viewpoint, the complexity of my scene might be different. Right? Like if I'm looking at a scene head on, I can see all these different objects. That's very different from like, you know, a giant wall obscuring everything. Right? Okay. There's a quick recap. We have two kind of big gains here, right? One is that we're only intersecting the triangles kind of near our ray, and the other is that we stop at the first time that we intersect. Okay? Those are the big two things that happen. Cool. And you see both of those reflected in our code here, right? Up here, we're kind of saying that if our line doesn't get anywhere near a box, just don't intersect at all. And this one's saying once you've seen something, you can stop this one. Yeah. There are all kinds of fun details that make this an even bigger heading. If you're intersecting a leaf, you have to be a little bit careful. Like in this horseshoe case, if I'm intersecting this leaf, but I'm intersecting with that horseshoe, I would say there is not an intersection. Because I know later on I'm going to intersect that. Otherwise you could create some weird branching issue. You need to take as actually just coming back to your question there, you need to take the direction of the ray into account, and you might have to flip which one's front and which one's back. Okay. And there's one case where you might divide by 0, and it's just something to be aware of, which is if your ray goes parallel to the side of the bus. So that's just something you might check for. Okay. So now we should go back to how to construct these things. And the key question is where to split, right? So once you decide on an axis, you have to decide where to put it. And there are a lot of different heuristics, right? So the simplest one might be to split right down the middle, but of course that doesn't make a whole lot of sense. So for instance, in this scene, right, I have a pretty sparse set of triangles over here, very dense set over there, so if I split it at the 50% mark, it doesn't really save that much computationally, right? I just made one giant leaf on the left. So another reasonable strategy is to split on the median. And this like kind of tries to balance an empty and dense areas. This I think is typically like if you take Piotr index class, like a computational geometry style course, this is probably the strategy they would recommend. But we actually know a little bit more, which is what we're using our KD tree for. Right? We're not, in this case, we're not doing machine learning. We're not like doing. There's not uniform probability that we're going to intersect our ray with any, like an arbitrary ray with an object here. We know where the camera is, right? And we know a lot of information like that. And so in fact, in graphics, people often say, well, I could try to balance this tree, or I could notice, for instance, if my camera is like right here, that maybe it makes sense for my scene to have a lot of cells in my KD tree here, because that's where the interesting detail is, right? Even if there's like lots of density back here, maybe that doesn't matter. I just put a giant box on it. And so there's all kinds of really clever things out there. The one that I think is most common, is left over from the 90s, is called the surface area heuristic. So what you do is you take your line for your split here, and you project all of your shapes onto that line, so they just become little intervals, right? And now you look at, so let's say that I have, this is hard to draw a picture of, but I'll give it a shot. So let's say I have a bunch of triangles like that. This is my splitting line, and I'm trying to figure out where to place it vertically. Or, no, that's a lot. But, I'd like to place a vertical splitting line, which means that I can move it horizontally along this line. So that's the better way to do it. And so here's what I'm going to do. I'm going to take all of the triangles, I'm project it onto the plane that's orthogonal to this line. Right, so we get a bunch of little intervals down here. And now I'm going to split evenly on the surface area that's taken up in this plane. Right, so in other words, like notice that these two triangles actually overlap a little bit. Right, so if I did the median thing, they'd be double counted there. But here we're just going to project onto this line and consider this to be one object. And the reason to do that is from the perspective of rendering, that's kind of roughly what's going on, right? Because you only, if you're like looking from here, then that's sort of the heuristic you want to use. And so this is some kind of heuristic that's roughly trying to capture the fraction of the rendered image as opposed to the fraction of the two-dimensional objects. Yeah.
Was always looking at this scene from like an angle.
No, like maybe you actually come up with a split very specifically to that angle.
And so,
Like for instance, maybe if your camera is looking off to the side, but for some reason you're constructing your KD tree this way, and you know that you're only going to render one image. That's the other thing. So you render from multiple camera angles, then you can not do that. Then maybe it makes sense, for example, to use the surface area heuristic always projected onto that plane or something like that.
so does, do they create a different mapping per like frame or different?
Typically not, right? So some of these strategies are specific to rendering one image, other ones are specific to a scene, and they depend on your task. Yeah, that's a great question. Anyway, if you like this kind of stuff, you're not responsible for it. You can work this kind of advanced topic, but there are all kinds of cool ways to come up with clever KD tree splits. And the thing to remember again is it's amortized, that like you might not have the most efficient KD tree in terms of depth, but what matters is render time, and those are not the same. Okay. So is it really important to optimize the splits? The answer is absolutely, yes, and there's all kinds of tricks that people do. So if you look at this guy, Ingo Wald from the 90s, had a PhD thesis on these tricks, and there are all kinds of hardcore efficiency considerations that people do to make ray tracing fast. Right? And then there are so many extensions for like tracing 4 rays at a time, and masking, and so all kinds of crazy tricks. Okay. So the pros and cons here are pros are that the coding is relatively simple for KD trees, easy to traverse, but the construction is a little tricky, especially if you use like these heuristics. It requires quite a bit of computation, right? So it could be that you need a pretty detailed scene for that. Okay, so that's the basic tree code, and we're going to talk about one more acceleration structure, which is kind of fun because it's going to lead into our next rendering topic, which is called array marching as opposed to ray tracing. And this is sort of halfway between rasterization and ray tracing. So the idea of ray marching is that I'm going to take my scene, and instead of dividing it recursively, I'm just going to fix some delta x, delta y, and delta z, and bin the whole world into a big grid. Right? So I'm going to put a big grid underneath the ground, and I'm going to say any object that intersects this box, I'm going to put in that box. Right? So in other words, I sort of have in this case, two-dimensional, or in 3D, a three-dimensional array, where every element is itself an array of all the objects that touch that box. Does that data structure make sense for one? It's pretty simple. Okay, so the ray marching algorithm does yet another kind of sneaky trick. It says, let's say I'm trying to render from this position here, right? So I'm going to first figure out the first place that I intersect the bounding box of my whole scene. That's this box here. And that intersects this particular guy. Yeah? And now, what's going to happen? Well, my ray is going to pass through this box, and then it's going to pass into one of the 4, or I guess usually one of the 4 neighboring boxes to this guy. Yeah? So I figure out which of the 4 neighboring boxes it intersects, and that's the next one that it intersects with. Right? And then if it intersects something in this box, I stop. If it doesn't, I figure out which of this guy's 4 neighboring boxes it intersects. I step up to that, and it intersects next. Now, what does this algorithm look like? You guys play with MS Paint? You know, and you draw a straight line between 2 points, and you get this kind of wiggly straight line thing. Well, take a look at the red voxels, which are the ones that I intersect with by red. Those are exactly the same as kind of pixelized or rasterizing this straight line. Do you see that? So in fact, the ray marching algorithm is somewhere halfway between rasterization and ray tracing. What it does is still ray tracing at the end of the day in terms of like the rendered image. But in order to do the ray scene intersection, it actually rasterizes the ray in the voxel grid of your scene, and just intersects with the things on the raster path. Really sneaky trick. Yeah? And in fact, all these algorithms for rasterization, which actually don't get used in the GPU anymore, which is a shame, like Bresenham's algorithm and so on, are relevant here. They're just really, really fast ways for drawing lines on grids. Yeah? So let's go into a little bit more detail. Right? So as input to this data structure is extremely simple, right? You just basically choose a grid resolution in X, Y, and Z. By the way, the resolution doesn't, I mean, I've drawn squares here, but they didn't have to be squares, they could be rectangles. And that's fine. And now I insert primitives into the grid. And typically, this is a data structure that uses a lot of pointers, right? Because I'll have a long list of all the objects in my scene, and then every grid cell will have a pointer to each of the objects that it touches. Incidentally, doing object cell intersection might be kind of a pain. So maybe I put a little bounding box around this object, and if the bounding box ever sticks over there, whatever. It's fine. And that's our basic data structure, right? So now, for every single cell along the array, if it returns an intersection, we stop. If not, we move on to the next box, and we kind of just play this like kind of Tetris game of moving along the screen. Okay. One thing to notice that happens a lot in the array marching algorithm is you get this computation, right? Especially if your cells are relatively small. Right? Like, so for instance here, this triangle belongs to these three cells, and so maybe we intercept the same triangle 3 times. And so there are 2 options out of that. One is to say like, whatever, which is often fine. That's option 2 here. Option 1 is to like put a little Boolean variable on top of each primitive and it says I already checked my intersectness and it does something. So now we're okay. So that's the basic thing. But one additional implementation detail here is, of course, if I have to be a little bit careful. Like this ray intersects this blue triangle, but it doesn't do so within the red box. So in this step of the algorithm, I would say it doesn't intersect. And that's to make sure that I get far enough back, because otherwise I might no longer see this blue guy. Does that make sense? You see what's going on here? Like if I return an intersection with this blue triangle, because this ray does eventually hit into it, I'd be in trouble because I didn't see the actual results. It's mostly a detail, but just like the kind of thing that shows up as a bug. So then the last question we should ask is do you intersect the array with every voxel? Obviously not. And in fact, you don't even have to intersect the array with every voxel along this line, right? I just have to start with the front one and work my way backward until I run into something really sneaky. Right. And so that's the very basic trick. And so actually doing this is actually, implementing this is exactly what you would have implemented if you made one of these old arcade games on the table in the 1970s. Right? They had these displays, which essentially, they weren't like what we have now, which are sort of like bitmapped images, but rather they had this laser that would fly around and trace out lines. And you really did have to come up with algorithms that raspberry stuff all along. And it's exactly the same kind of trick here. So if you read an old school graphics textbook, you'll see all kinds of matches doing this fast. I think the reality is you don't have to do this particularly fast because it's still much more efficient than actual ray tracing procedure, but it's kind of fun to know that it exists. Right? And the basic idea here is that if I look at the pattern of places that I intersect, obviously they're evenly spaced, right? Like the t values where I intersect all the vertical lines are spaced by dt. Similarly with the red planes. And so it's very easy to detect cell crossing to figure out which direction it is. Right. And so there's the little trick, right? I say, like, I'm at some wall, I figure out the next t intersection, the next x intersection, the next y intersection, and take whichever one is closer. Yeah? And this is actually an example of what we call 3DDDA, which stands for the three-dimensional digital difference analyzer, which was the fancy name people had for this style of raster graphics back in the day. Yeah? And so the pseudocode looks something like this, where you create your grid, you insert all your primitives, then for each ray you find the first cell that it runs into, and then you just kind of walk along this grid one stepping stone at a time until you finish. And in fact, one of our colleagues here actually managed to visualize it, and you can see what's going on. So for instance here, you see the sequence of rays, the sequence of cells in this ray. Does algorithm make sense to everybody? I think it's a sneaky trick. I would say that asymptotically, it's hard to say much about this algorithm. Like you could have bad luck and really actually this is quite computationally expensive. Your cells are too small. But it's extremely easy to code and kind of fun to look at. Right? And so the advantage is it's really easy to construct this thing, right? You're just binning stuff. There's no recursion involved, it's easy to reverse. But you might end up with like a giant grid on top of your scene where most of the cells are empty. You still got to walk through them. Okay. So very briefly, for the last 5 minutes of our class, we'll suggest what's next. A philosophical question we should ask. So we've now done a lot of work intersecting arrays and objects. And our next goal is going to be to shape them in ways that aren't just diffuse. And of course, a key question you should ask, is does ray tracing really simulate physics? The answer is no, right? I mean, physics, the photons come out of the light and go to you, right? And we're tracing back to the light. Yeah? And so what we're doing, the term for the algorithm that we've explored so far is something called backward ray tracing, right? And this is really a bunch of tricks and approximations, right? And so, for instance, transparent objects create a big problem because refraction leads light to go on these nonlinear paths that we can't really trace back. So what we're going to start to think about is a different technique, which is used, for example, to create images like this. So you guys see that this is some crystal cube here, and the light is coming down and it's getting focused by the walls of the cube before it hits the bottom. Right? So the backward ray tracing algorithm of drawing a line back to the light isn't going to help you here because the line back to the light actually bends when it goes to the interior of the cube. And that's not something that we can solve for. And so we're going to talk about an advanced technique called photon mapping, where now I'm going to forward trace on the light to kind of figure out where the photons go. And this will show us tricks like caustics. Right? And so that's the basic idea here. Is we're going to start from the light source, scatter lots of little photons, and then kind of smear their influence to points nearby. And so essentially, I'm just mentioning it now because I want you guys to all think about it for next week in terms of how would you actually ray trace a caustic underneath. If that problem is too easy, by the way, a really fun problem to think about, that's a research problem in my field, so I know a little bit about it, is let's say I have a piece of glass. So I have a light bulb here. And now I put a piece of glass, and then I have a plane. And I draw a picture over here. Right? Whatever. Here's a cat. And what I'd like is to design a piece of glass so that the caustics look like a cat in the shadow. That's our. But anyways, for the next time we'll just talk about drawing caustics. And if you want a really challenging thing to think about, you should think about how to engineer a caustic given a piece of glass and a bin. But anyway, with that, I will see you guys next week. Don't forget your homework is due this evening. Your next one should already be out. And yeah.